Hey team, welcome back to lesson 2 of 2.4 atomic structure and bonding. Today's learning objective is to be able to draw Lewis structures for covalent molecules. So before we begin, I thought I would just start with recapping what the three main types of bonding are in chemistry. First of which is ionic, the second of which is covalent, and the third of which is metallic. So just to quickly go through what they are. So ionic bonds are formed between a metal and a non-metal when the metal transfers electrons to the non-metal. So the metal loses electrons, the non-metal gains the electrons, and they form a bond. Now we'll go through in a lot more detail a bit later in the topic of this, but all types of bonding in chemistry are electrostatic in one way or another. Electrostatic simply means an attraction between a positive and a negative. So when we talk about an ionic bond, that electrostatic attraction is between the positive ion and the negative ion. Covalent bonding is the second type of bonding, or it's just another type of bonding, and that is the sharing of electrons between two non-metals, and we're going to talk a lot about this today. So just before we kind of move on from that, I'll explain. I said every bond had an electrostatic attraction. So the electrostatic attraction in a covalent bond is between the positive nuclei of each atom and those negative bonding electrons. And so that's what creates that covalent bond. The third type is metallic bonding. You may not have done a lot on metallic bonding actually, but we will be doing a lot later on in the topic. So metallic bonding is between the metal cations and the delocalized electrons, and the electrostatic attraction there is the positive nuclei of those metal atoms / cations and those delocalized negative electrons. So just to recap, all bonding in chemistry is electrostatic in some way, which means an attraction between positive and negative. And there are three main types of bonding in chemistry: ionic, covalent, and metallic. And it's kind of the focus of this topic, really, this whole standard. And we'll be going through this in more detail later on. Where we're headed today is covalent molecules. So a little bit more on covalent bonding. Covalent bonding is extremely strong, and we have evidence for this in our everyday lives. If you go and grab some ice out of the freezer, and we all know from prior knowledge that ice is frozen water, if we leave it to melt, the water becomes liquid water, right? And so it's still water, so it hasn't actually changed in its molecular structure. So that kind of gives us a bit of like, what's going on here? Because the water itself hasn't broken. So these bonds between the hydrogen and the oxygen haven't been broken when it's melted. So therefore, the covalent bonds are not breaking. And that's purely because covalent bonds are super strong, and something else must be breaking instead. And in year 11, you actually learnt about this. We learnt that between molecules, so here's water, and between the water molecule is a weak type of force called an intermolecular force. And these intermolecular forces are weak, and they're what actually breaks when water melts. So from when it was solid to lots and lots of water molecules arranged close together, they break during melting, and so the water stays intact. So the covalent bonds themselves, the sharing of electrons between atoms, are very strong and don't break, and the weak intermolecular forces between the water molecules are what breaks. If you're struggling with this weak intermolecular force concept, don't panic. We're going to do a lot on this later on. What we're kind of focusing on today is how do we know water takes this arrangement? And that's what we're going to talk about, Lewis structures. So more on that in a second, but just to give you a little overview, oxygen, you can see here, is sharing 2 electrons with hydrogen. Oxygen's a non-metal, hydrogen's a non-metal. They're sharing electrons, and therefore they have covalent bonds. Covalent bond and covalent bond. Why do they do this? The same reason that atoms form ions, and that's to gain a full valence shell, and so they just do it by sharing them instead. So hydrogen only needs 2 electrons, so it's happy, it's got its 2 electrons. Oxygen needs 8 electrons, it's happy, it's got 8, and this hydrogen's happy too. So I guess more on this. Let's look at Lewis structures. So We know from probably seeing pictures of water many a times, and we've just accepted that water takes this kind of V shape. So why does it? Why does it take this V shape? And so we start by looking at a Lewis structure. So Lewis structures are only done for covalent molecules. Now, you've heard me say before that the word molecule is purely used for covalent substances. Okay, so that's a word you need to get used to, that the word molecule is for covalently bonded substances. In this section of the topic for Lewis structures, we are only concerned with the valence electrons, okay? Because valence electrons are what take part in bonding, and they're the part of the atom that'll be getting shared between atoms. So you can see here, here's all the valence electrons of some of the atoms of the periodic table. Now, most atoms require 8 electrons to become stable. We know that 2 exceptions are hydrogen and helium. They require 2 electrons because they're in energy level 1. And there's also another exception which I'll get to at the end of this topic. So there are certain rules for completing Lewis structures. Okay, so step 1 is to add up the number of valence electrons. Step 2 is to work out the central atom. There are 2 methods here. You either look by symmetry. So if we're looking at, for instance, an example of H2S, okay, S is by itself, so we would make that the central atom. Okay, so that's one way, it's the easiest way, but we can't use that all the time. So we have to have another way of doing it. And so the second way is by saying the most electron deficient. And deficient means doesn't have enough. So hydrogen has 1 electron, needs 1 to be stable, to get to 2. Sulfur has 6 electrons and it needs 2. So because it needs 2, it's the most electron deficient. So we can further confirm sulfur is our central atom. The next step is to place 8 electrons around the central atom. Okay. And the last step is to make double bonds or multiple bonds if you run out of electrons. Now, rules are great, but they don't make any sense until you've done an example. So let's go through and do some examples together and they'll make more sense. Please note, if you look at some stuff online, this step here will be different. Some people choose to show which atom that the electrons have come from. This is not a requirement for NCA, and I tend to find it's easier not to worry about that. So, we're going to start with water, lovely water, H2O. So let's start by counting up the valence electrons. This is where it's really good to have your knowledge from that first video I made on periodic tables. Group numbers, they're vital here. Oxygen's in group 16, so it's got 6 valence electrons. Hydrogen has 1, there are 2 of them. This gives us a total of 8 valence electrons. Okay, so we're only concerned with valence electrons. Step 2, finding out the central atom. So oxygen needs 2 electrons to become stable. Hydrogen only needs 1, so oxygen's more electron deficient. And there's also 1 of it, so via symmetry, so oxygen's our central atom. Okay. So the next step, step 3, is to put 8 electrons around the central atom. So 1, 2, 3, 4, 5, 6, 7, 8. You can see I've done that there. I'm not awfully neat, but try and be as neat as possible. I think crosses are messy. If you're adamant you want to do them, do them. I'm not going to argue with that sort of thing. But dots, I think, just look a bit better. Just make sure that they're clear diagrams. There's nothing worse being a marker and not being able to read a diagram properly. Okay, so then the next thing that you do is add in the other atoms. In this case, we can just plonk hydrogen either side, and this hydrogen's now got 2 electrons, this hydrogen's got 2 electrons, and our oxygen has 8. So all 3 atoms have full valence shells, and therefore that is our Lewis structure of water. So let's now do some more examples. So let's try NH3. Nitrogen's in group 15, 5 valence electrons. Hydrogen in group 1, 1 times 3, that gives us a total of 8 electrons. The central atom, nitrogen's by itself, so it's going to be that, but we also know, we can see it needs 3 electrons to be stable. Hydrogen only needs 1, and therefore that confirms nitrogen is the central atom. I'm just going to keep going now and complete this Lewis structure. So we've got 8 electrons, so let's put them on. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and I can just put 3 hydrogens at any spot, doesn't matter. Well, next to the 2 electrons, obviously. So you could have done an H at the top here. That would be fine as well. And so we've got NH3. The nitrogen's got 8 electrons, so therefore has a full valence shell and is stable. And each hydrogen has 2. So all is happy. Okay, moving on. We can skip past that. Let's try CH4 now. Okay, carbon's in group 14. 4 electrons, hydrogen in 1 times 4 gives us 8 electrons. Central atom's going to be carbon, it's by itself, and also it's the most electron deficient. Hydrogen needs 1, carbon needs 4. Put 8 electrons around your central atom. Oops, a couple of these are a bit ugly, that's alright. Add in your hydrogens. Each hydrogen has 2, each carbon has 8, well the one carbon has 8 electrons. All are stable, and that's the Lewis structure for carbon. For methane. So, perfect. Multiple bonds now. Okay. Multiple bonds happen when we run out of electrons, essentially, to make a single bond. So, let's run through some examples. So, CO2, let's just do this together. I don't know why that line's appeared, but we'll just carry on. Carbon, group 14, so 4 valence electrons. Oxygen, group 16, so 6 valence electrons. So this gives us a total of 16 electrons. Okay, central atom will be carbon, because carbon needs 4 electrons to become stable. Oxygen only needs 2 electrons to become stable, so carbon's the most electron deficient. So what I'm going to do here is put 8 electrons around. 1, 2, 3, 4, 5, 6, 7, 8, and then I'm going to add in my 2 oxygens. Now I tend to put them on either side just due to symmetry. It makes life much easier. Okay, so I've got 2 oxygens either side, and I've used 8 electrons, which leaves me 4 for each of the 2 oxygens. Now if you're counting here, you should be able to see that carbon's got 8, but each oxygen's only got 6, and that's an issue because that means that the oxygens are not stable. So we've run out of electrons, and therefore we need to have a multiple bond. So what happens is these electrons from here come down and create a multiple bond, and these electrons from here come down and create a multiple bond. So what you end up having is 2 double bonds in this structure, like so. Now this oxygen's got 8 electrons, this oxygen's got 8 electrons, and the carbon's got 8 electrons, so they're all happy. So this skill is a bit trickier, takes a bit of practice, so don't panic, we'll keep doing some more examples. Let's try N2 together. Okay, nitrogen's got 5 valence electrons because it's in group 15 times 2, that gives 10 electrons. Don't have a central atom this time because you've only got 2 atoms, so we just put 2 in the middle and then divide the rest up. So 3, 4, 5, 6, 7, 8, 9, 10. Should be seeing here that we've got an issue because we've run out of electrons, and neither of them are stable because they haven't got 8 electrons. So we're going to move a pair of electrons and create a double bond, so let's do that. And what you'll notice is it hasn't worked. Okay, we've still got an issue. Okay, this nitrogen's only got 6 and this one's got 8, so this one's happy, this one's not. So we need to make another multiple bond. This pair are going to move in here. When you draw this, be careful, the bonds should be horizontal. Okay, so 3, 1, 2, 3. You can do, by the way, I haven't mentioned yet, you can do a straight line instead of 2 dots when it's between 2 atoms. Up to you what you prefer, but you must leave your lone pairs, which is the ones without an atom, as dots. So now what you can see is this nitrogen's got 8 electrons, this nitrogen's got 8 electrons, both are now stable, and that is the Lewis structure for N2. So how about HCN? Bit of a mean example, bit of a hard example, but I know you